Today we're going to talk about host-side memory model. In OpenCL, both the host side and the device side have memory spaces we can use to store data and perform computation on them. But OpenCL specification has few specific requirements how we allocate data and how we move them. We can conceptualize the reading and writing of buffers and move data to and from the device, but these are actually not explicitly required. We have different ways to ask the OpenCL framework to allocate memory spaces and move data. The memory management examples we're going to see attempt to show you that some of the subtleties of real implementations. We know that the devices operate with memory systems that are often separate from the main memory on the host side. We're going to start today to talk about the host side memory model, where we can use that to provide ways to better utilize the memory spaces on the host and on the device side. The OpenCL host side memory model supports a so-called relaxed consistent model, where the global synchronization of memory is defined only with the completion of events. Some newer OpenCL specifications have optionally consistency guarantees as in high-level languages. But today we're going to focus on the majority of these relaxed consistency model. We're going to look at some examples of memory object creation, and we're going to show you how to use memory flags to define or specify how we want the data to be allocated and how to initialize them. We're going to show you examples of writing and reading buffers and how to manage these buffers, in some cases migrate these memory objects. Also, we're going to show you how to use host accessible memory. We talked about memory objects in the past. The memory objects are the instances that we use in a context to work with data. Oftentimes, we want to provide synchronization among these memory operations, and we use, for example, wait for events, which is a little bit different from a marker, which this is really not an event. These events are in the queues for a device, and these devices will take different memory operations, put it into the queue, and perform the corresponding operations. And the memory objects host the execution of queues for a specific set of triggering events that have completed. We're looking at here three types of memory objects, and mostly we're going to look at buffers in this lecture. Although we have touched upon image object in the previous lectures, pipes is something new in OpenCL 2.0, and we're going to spend a dedicated session on that. Buffer objects in general are one-dimensional arrays in the traditional CPU sense. You can use buffers for initializing your data, and also for computation, and of course for storing the computation result. It's similar to malloc, use the C program, but we use create buffers in very different ways as in a C program. Buffers can contain any scalar type data, vector data, or user-defined structures. Images are dedicated buffers designed for accessing image data. So the data in the image objects follows specific format so that the image-related operations can be performed very efficiently. Pipes are used to organize data in a first-in, first-out FIFO structure. We can pass data from one kernel to another kernel. But again, today's lecture, we're going to talk about buffers exclusively. We can use different memory flags when we create buffer and when we operate them. Moving data at runtime is inefficient. So OpenCL attempts to provide options as part of the commands to suggest where the data is allocated and when and where the data should be moved. We used CL create buffer API to create a buffer object. And this table lists the memory flags that we can use to define the attributes of the buffer object. We're going to go through this table very briefly, and we're going to show you examples later. So we can see this table has memory flags, and the first three memory flags are somewhat familiar to us. Read, write, write only, and read only. These three memory flags are used to specify the types of access that are allowed by a kernel. And note that the memory object is used primarily by the kernel. The next few memory flags, for example, CLMem use host pointer. This use host pointer is to tell the OpenCL runtime that we're going to use a host pointer as the storage for the buffer. So the buffer is going to be allocated in the host memory space. Although in real implementation, the OpenCL depends on the vendors, the device can choose to cache the content to device memory if it turns out to be more efficient. And then kernels can use the cached copy on the device when a kernel executes. The next option, CLMem allocate host pointer, is to allocate buffer storage in the host accessible memory. Note that we are trying to allocate buffer, and this buffer is supposed to be accessed by the kernels executed on the device. Allocate host pointer is to allocate buffer storage in some space that is accessible to the host. If the OpenCL runtime allocates the buffer on the host memory, it is certainly going to be accessible to the host. If the OpenCL runtime determines to allocate the buffer stage on the device side, then that part of the device memory has to be accessible to the host. So that's what this allocate host buffer is about. The next option, CLMem copy host pointer. This is to initialize the buffer with data from referenced by the host pointer. So you're going to be seeing this copy host pointer coupled with a pointer to the host memory so that the OpenCL runtime knows how to get the initial data, which is pointed by the host pointer, and initialize the buffer with that data. The next three options, host write only, host read only, host no access, are to specify what kind of accesses are allowed by the host towards the memory object. When OpenCL creates a memory object, they are allocated in global memory space visible to all the devices in a context. So this is the goal of these memory objects. No matter where we physically allocate them, they need to be visible to all the devices in that context. In reality, the devices in a heterogeneous system may not share address spaces or may have physically separate memory units. So the OpenCL runtime has to create multiple copies of the data for each device. And that's the job of the memory management. Even in a shared memory space, the data may have duplicates in different cache hierarchy for the goal of improving the access efficiency. It is the OpenCL's relaxed consistent model that we do not allow multiple kernels to modify the objects at the same time. And reading data while the other kernel is modifying is undefined.